Okay, by now you should understand that acceleration is a change of velocity over a given amount of time. So when things are speeding up and when things are slowing down, the velocities are changing, so those objects are undergoing acceleration, whether positive or negative. So now what we're going to discuss is the acceleration due to gravity, which is also known as, or which can be known as free fall. Okay. We all know that gravity is what causes things to fall, and if there's no restraints on the object that has fallen, there's no friction, there's no air resistance, and it's only gravity that's causing the object to fall, the object is said to be in a state of free fall. Okay. Now, in the regular world, in the real world, there's going to be air resistance, yada, yada, yada. But in science, when we study these things, we have what's called a vacuum where we remove the air, and so there is no air resistance. Regardless of their weight and size, acceleration is going to be the same for those objects that are in free fall. So no air resistance, none of those things occurring. And that value of gravity is 9.8 meters per second squared. What that means is that for every second, the velocity is going to change by 9.8 meters per second. So, for example, at the initial start, time zero, velocity zero, the initial velocity, an object is dropped. After 1 second, that object is going to have a velocity of 9.8 meters per second. After 2 seconds, it's now going to have a velocity of 19.6 meters per second. Right? And so on and so forth. So for every given measurement of time, we would measure we calculate 9.8 meters per second squared times that time to figure out the velocity of that object. If we were to do the ticker tape lab with the automobiles or the little cars going down a ramp, how these blue dots are arranged is similar to what we would see on the ticker tape. At the beginning, we would see them real close together, and then as you guys noticed when we did the velocity lab, the faster the object went or the cars went, the more spread out the little spots were. And so what would happen for the ticker tape lab or the ticker tape activity with the acceleration is as time would go on, the dots would get further and further apart because the speed is continually to increase. So this is what happens when things fall. When an object is going down, the acceleration due to gravity is negative 9.8 meters per second squared, just because down is generally negative. Up, the initial velocity when objects fall, not when they're thrown down, but simply when they are dropped, or they just fall, not being thrown, this initial velocity, remember this 0 here means v naught, it's the initial velocity, is actually going to be 0. When we throw something, the final velocity is not going to be 0. This final velocity is the moment before impact. So that split second before something hits the ground, the final velocity is not equal to 0. And that's what this little equal sign with the slash means. Now, when we have an object being thrown up, the acceleration due to gravity is going to be positive 9.8. Okay? Now, a lot of people think, oh, well, positive acceleration, that means it's going to be speeding up. But if you throw something into the air, hopefully you recognize that not speeding up, it's actually going to be slowing down. So what we have to remember is that the velocity is downwards, the acceleration is upwards, so it's going to be opposite. In this instant, the initial velocity is not equal to 0 because we have to throw it up or throw the object up. At the top, at this very tippity top, which is called the apex, which we'll get to more in detail later, this final velocity is going to be 0. There's a split second, and you'll notice it if you throw something in the air, there's like a split second, less than a second, where the object is not in motion, so there is no velocity. Okay. These are the important variables that we use when we have constant acceleration. So the acceleration is going to be the same throughout. X is going to be a measurement of distance, and we measure it in meters. T for time, which is going to be in seconds. The initial velocity is going to be meters per second, and the final velocity also meters per second. So remember this V naught and VF are initial velocity, final velocity. Acceleration is meters per second squared. And of course, if an object is falling, the acceleration is due to gravity, so we use a G, and that's going to be negative 9.8 meters per second squared. Okay. In physics, there are 4 big equations that we use for constant acceleration. So this is very, very, very important. The first one, we have VF, which is the final velocity, and that's going to be equal to the initial velocity plus the acceleration times time. Second one, we have x, which is our distance, is going to be equal to the final velocity plus the initial velocity divided by 2 times t. We have x again, so our distance again is equal to the initial velocity times time plus the acceleration times time squared divided by 2. And then this one, notice, is the final velocity squared is going to be equal to the initial velocity squared plus 2 times acceleration times distance. Now, if you notice that in each one of these, it's actually missing one of these variables that are very important for our acceleration. Okay, in the first one, we don't have distance. Okay, so there is no x here. In the second one, we have no acceleration, no a. No final velocity here, and then over here, if we don't have time, but we want to know what the any of these other variables are, this is the equation we would use. Now, the examples and the problems you're going to see for this part of physics, these constant accelerations, you have to be very careful in analyzing what you're given, what you're looking for, to help you determine what equation you would use. Okay, so I do want to go over a couple of examples with you just to make sure you're following along. Okay, so first thing I want you to do is we're just going to identify which one of these 4 equations are we going to use to solve this problem. Okay, so if a car slows down from 45 meters per second to 30 meters per second over 6.2 seconds, how far does it travel in that time? Okay, say you're driving on the road and you see brake lights up ahead, so you know you need to start slowing down. You start to brake over 6.2 seconds. You're going to go from 45 meters per second to 30 meters per second, and we want to know how far are we going as we're slowing down. Okay, so here's what we need to figure out. What do we have? We have 45 meters per second, we have 30 meters per second, we have 6.2 seconds. Now looking at this information, it's like, okay, well, what actually is it? So a car slows from 45 meters per second, okay, to 30 meters per second. So that must mean the 45 meters per second is our initial velocity, and our 30 meters per second is going to be our final velocity. Hopefully you guys recognize that 6.2 seconds is time. So we start at 45, we slow down, oops, not to 40, but to 30, and it's going to happen over 6.2 seconds. What are we looking for? How far does it travel? That means we're going to be looking for distance, which means we're going to be looking for x. So when I'm looking at my variables, the one thing I don't have is acceleration. So the equation I'm going to use is the second one where I'm not given acceleration. Acceleration is not involved in this equation at all. Second example, again, all we're doing is identify which of those equations do we use. A ball is rolling up a hill, accelerates at negative 5.6 meters per second squared for 6.3 seconds. If it is rolling at 50 meters per second initially, how far has it rolled? What we have is negative 5.6 meters per second squared. 6.3 seconds. 50 meters per second. You recognize that it says accelerates at this, or you recognize that there's a meters per second squared. That is acceleration. 6.3 seconds is time, and it tells us that it's rolling at 50 meters per second initially. How far has it rolled would be our distance, which is x. So we have acceleration, we have a time, we have initial velocity, we have a distance. The one thing we don't have is a final velocity. So the equation we would be using would be the third one with no final velocity, no VF. A bowling ball is thrown at a speed of 6.8 meters per second. By the time it hits the pin 63 meters away, it is going 5.2 meters per second. What is the acceleration? Okay, so we have 6.8 meters per second, 63 meters, 5.2 meters per second. We have an initial velocity, we have a distance, and we have a final velocity. What are we looking for? We're looking for acceleration. Equation that we use? Number 4, the one with no t. Okay, so that was just practice on how to identify which equation to use, which if you can figure out which equation you're using, that is half the battle. Last one. An onion falls off an 84-meter high cliff. Not sure why an onion, but there you go. How long does it take to hit the ground? Now, if we're looking at this problem, it only gives us one number, 84 meters. I'm like, how in the world are we going to solve anything with 84 meters? But then we have to remember, it's falling. Okay, so when things fall, they fall because of gravity. Acceleration due to gravity, we know that. That's a constant. And we also know that it wasn't thrown down. So that means we know that the initial velocity is going to be 0. Our x, our distance, is 84 meters, 0 for our initial velocity, and negative 9.8 meters per second squared for our acceleration. How long does it take to hit the ground? Indicates that we're looking for time. So the equation we need to use is the one where we do not have the final velocity. Next part I want to go over is a couple examples, the same exact problems, except this time we're actually going to solve them. So I'm going to go ahead and transfer the information that we already figured out when we were trying to figure out which equation to use. So the first one, we're using equation 2 because we're not given an acceleration. Okay, so I have my equation. Since we're looking for time, or excuse me, since we're looking for distance, I don't need to rearrange the equation at all because x is already by itself. So all I'm going to do is plug in the numbers. If you notice, I went ahead and used 40 here instead of the 30 that's in the problem. That's my mistake. Okay, so we plug in our numbers. This is in parentheses. This is on top of the denominator, so it's a numerator, so we're going to do that first. So we're going to have 85 over 2 times 6.2 seconds. 85 divided by 2 is going to be 42.5 times 6.2 seconds. That means that this car is going to travel 263.5 meters before it actually reaches this speed, or this velocity. Next one, I already have a little bit there. A ball rolling up a hill accelerates at negative 5.6 meters per second. This is what we're given. Looking for x, so I'm going to leave x over here. Just plug in my values. Plug in, squared this, got this, multiply this, got this, divided by 2, got this, multiplied 50 times 6.3, got this. This is negative because the acceleration was negative, which means the ball is slowing down. So we get the ball goes 203.9 meters before it actually, when it goes 6.3 seconds. The bowling ball thrown at a speed, we had all this information. We were using equation number 4. But if you notice, this time we're looking for acceleration. That's the a. So that means we need to get the a by itself. Right now, these are all multiplying, and this is just adding in. So these are like super best friends at a party, and this is like meh, kind of friend at a party. Who are we going to say bye to first? We're going to say bye to our kind of friends first. So we're going to subtract out the initial velocity from both sides. So we're going to get final velocity squared minus initial velocity squared is equal to 2ax. Now we're going to go and say bye to our best friends, 2x. Because they're multiplying, we need to divide. What I do to one side, I do to the other. So I have vf squared minus v naught squared over 2x equals a. Now my a is by itself, so I'm going to go ahead and plug in my information. Remember to square your velocities. This is very important. Okay, and I get negative 0.15 meters per second squared. Now, if you're not sure if it's negative or not, if that makes sense, we need to look at what we were given. An initial velocity of 6.8 meters per second, and then after it hits, or when it hits the pins, then it's going 5.2 meters per second. So it did slow down, so a negative acceleration does make sense. Last one I wanted to go over was the weird onion one. An onion falls off an 84-meter high cliff. How long does it take to hit the ground? Remember, we had to use this one. We were looking for the time. Now, if you notice this equation, we have time in two places. So that can be some crazy math that we learned a couple years ago, but probably don't remember. But then I'm like, hey, wait, my v naught, my initial velocity is 0. Anything times 0. So this t times 0 is going to be 0. And 0 plus anything is going to be this anything here. So I'm going to go ahead and just ignore that part. I don't need it. It's not important. So then I'm going to be left with this. I'm like, okay, this is a little bit easier. I only have one t. So right now I have this mess divided by 2. So I need to get rid of the 2 first. So I multiply 2 on each side. So I have 2x equals at squared. I need to get rid of the a, so I'm going to have 2x over a equals t squared. But I don't want time squared, I want time. So I need to find the square root. Plug in my numbers. That onion is going to fall for 4.14 seconds. And and that's going to be equal to time, not to acceleration. What I'd like you guys to do is, on the website, there are practice problems with answers linked. Go ahead, go through a few of those until you're comfortable, check your work, ask for help if you're not getting it before you start the assignments, just to make sure you're on the right track.